Welcome to the Himalayas, where humanity has just completed one of the highest and most difficult to build tunnels in the world, the Atal Tunnel. This is a mega project with a total investment of 3,200 crore rupees, equivalent to about 438 million US dollars. Here, engineers excavated right through the center of the rocky mountain mass at an altitude of over 3,000 meters above sea level, creating a tunnel that is 9.02 kilometers long. This structure is officially recognized as the world's longest single-tube highway tunnel at an altitude above 3,048 meters. The Atal Tunnel has completely transformed the transportation network in one of the regions with the harshest terrain and weather conditions. So, what mechanical methods and construction techniques did the engineering team use to deal with the massive volume of rock and soil inside the mountain? Let's analyze the construction process of the Atal Tunnel in detail in today's video. If you find this video helpful, don't forget to like and subscribe to the channel to keep following our in-depth analyses of large-scale engineering projects. On India's infrastructure map, the Leh-Manali highway is a crucial transport artery, connecting the Lahaul-Spiti region with the rest of the country. However, this transport system faces a massive physical barrier at the Rohtang Pass. Situated at an altitude of 3,978 meters, this pass constantly endures heavy snowfall. As a result, the Rohtang Pass is forced to shut down entirely for 6 months during the winter every single year. When this single lifeline is cut off, the entire Lahaul-Spiti region falls into a state of absolute isolation. And even in the summer, when the pass reopens, vehicles still lose 5 to 6 grueling hours navigating its steep, winding, and dangerous switchbacks. This infrastructure bottleneck not only drives logistics costs to exorbitant levels, but also severs supply chains, severely crippling the economic growth of the entire region. To definitively solve this problem, the engineered solution was to drill a tunnel straight through the core of the mountain massif. This mega project not only maintains a seamless flow of traffic 365 days a year, but also directly shortens the physical distance by 46 kilometers, saving 4 hours of travel time for the entire journey. For modern mountain tunneling projects, tunnel boring machines, TBMs, are usually the preferred solution. However, at the Atal Tunnel, engineers decided to completely eliminate this equipment. Why is that? The answer lies in the complex geological structure of the Himalayas. For a TBM to operate efficiently, the rock strata need a certain level of uniformity and must be accurately surveyed beforehand. However, hidden inside this mountain mass are unpredictable underground geological faults. Furthermore, the layer of rock and soil above the tunnel, the overburden, reaches a thickness of up to 1.9 kilometers, generating massive physical pressure. If a TBM entered a fault zone and got stuck under the crushing pressure of this 1.9 kilometers of rock and soil, rescuing the equipment would be almost impossible, leading to the stagnation of the entire mega project. In addition, the temperature in this area has extreme fluctuations, from 25 to 30 degrees Celsius in the summer, plunging to minus 30 degrees Celsius in the winter, creating major challenges regarding thermal stress. Faced with this physical barrier, the engineering team needed a highly flexible construction method, allowing them to assess and adjust their handling techniques for every single meter of rock excavated. The most optimal solution was to discard the TBM and instead apply the drill and blast method combined with the new Austrian tunneling method, abbreviated as NATM. As soon as the blueprints were approved, construction commenced simultaneously from both directions, the south portal and the north portal. The NATM construction process at this project was repeated meticulously by the engineers. First, a multi-boom jumbo drill bores a series of deep holes into the rock face ahead. Then explosives are loaded and detonated with precise control to fracture just the right amount of rock. As soon as the dust is extracted, excavators immediately move in to clear tons of fragmented debris, exposing the new tunnel face. Next comes the golden moment of NATM. Instead of waiting to pour massive concrete molds, engineers use high-pressure nozzles to immediately spray a very thin layer of fiber-reinforced concrete, measuring only 25 to 50 millimeters, covering the entire rock surface. This artificial skin prevents air and moisture from weakening the rock seams, keeping the tunnel walls in their original state. Then, to lock the rock face in place, they drill through the shotcrete and install steel rock bolts, ranging from 5 to 9 meters long, deep into the mountain core. These steel rods act like giant nails, pinning the loose rock layers together, transforming the natural rock face into a solid, load-bearing arch. Finally, optical sensors are installed to monitor every single millimeter of mountain movement. This data is instantly sent to the control center, where engineers calculate and decide the concrete thickness and the amount of explosives for the next cycle. This sequential process advances with extreme caution. To complete this horseshoe-shaped tunnel, wide enough for 2 lanes of traffic, the project consumed a staggering amount of materials: 14,508 tons of steel, 237,596 tons of cement, and successfully excavated 1.4 million cubic meters of rock straight from the core of the Himalayas. But even a superior method like NATM had to face the harshest physical barriers when advancing deep into the core of the Himalayas. When the tunnel excavation reached the Seri Nala geological fault zone, the engineers' drills punctured a massive underground water pocket hidden deep within the rock layer. Immediately, water flooded into the construction space at a flow rate of up to 110 liters per second, equivalent to having to handle nearly 400,000 liters of water pouring down every hour. This torrent carried tons of mud and crushed rock, threatening to bury all the equipment and collapse the tunnel wall structure. Faced with the risk of total collapse, the engineers were forced to pause the excavation process. The first thing they did was urgently set up a high-capacity pumping station system along the tunnel route to continuously suck water and mud out. But that was only a temporary solution. To truly drill through this muddy area, they had to implement a support arch engineering system known as pipe roofing. First, to prevent the tunnel ceiling from collapsing onto the workers, a series of large-diameter steel pipes were driven by hydraulic drills through the mud, penetrating deep into the unexcavated soil ahead. These steel pipes were placed close together in an arc shape, creating a giant load-bearing steel protective umbrella right overhead. Immediately after, to seal off the gushing water, they could not use regular cement because it would be washed away by the water instantly. A chemical solution was activated. The engineers injected a special chemical, like polyurethane, at extreme high pressure straight into the cracks. This chemical has the property of expanding and instantly hardening upon contact with water, acting like a superglue that not only stops the underground water flow, but also welds the fractured geological structure into a solid block. Only when the steel umbrella was stable and the water flow was tightly locked could the excavator be allowed to move in. But they could not dig quickly. The construction process could only inch forward half a meter at a time, and instead of spraying a thin concrete layer, the engineers had to use heavy steel ribs joined close together to passively support the tunnel walls. The underground pressure was already terrifying, and the surface limitations were even more fierce. Winter weather dropping to sub-zero temperatures caused the Rohtang Pass to be blocked by snow, completely cutting off the supply chain from the northern portal. The construction crew was pushed into a corner where they had to handle 3/4 of the project's workload from a single direction. It was this extreme complexity of both geology and logistics that forced the engineering workforce to trade up to 4 grueling years of labor just to overcome a fault section measuring a mere 550 meters in length. After conquering the Seri Nala fault, the final puzzle was operational safety. How do you evacuate a single-tube tunnel over 9 kilometers long? Instead of excavating a costly parallel tunnel, engineers designed a heavy concrete slab cutting horizontally across the horseshoe cross-section. The upper level is the main traffic deck, while the space underneath is an independent emergency escape route. Every 500 meters, there is an escape trapdoor. In the event of a fire, trapped individuals simply climb down into the bunker to be completely isolated from toxic smoke. This smart spatial design was the final piece to complete the mega project. On October 3, 2020, the Atal Tunnel officially opened to traffic. The blizzard barrier that blocked the Rohtang Pass for 6 months every year was completely eradicated. The new route shortens the distance by 46 kilometers, wipes out 4 hours of travel time, and connects the region continuously 365 days a year. The Atal Tunnel is a magnificent testament to mechanical ingenuity, proving that humanity can use technology to conquer the harshest mountains on the planet. If you found this video informative, don't forget to like, subscribe, and leave a comment. See you at the next mega project.